Hey guys, our video for today is going to really extend what we learned about the trig ratios yesterday and using the inverse functions to solve equations. The title for today is Special Right Triangles. Again, this is a topic you should remember from geometry. So I'll let you kind of ruminate on that for a little while. And we're going to do some problems here that you may have done in eighth grade or geometry when you did the math, but we'll be reminding you of them. And if you struggled on them at that time in those classes, you should be able to nail those down right now. So let's proceed forward. And the first thing we're going to talk about is what we call angles of elevation and depression. And these problems are an application problem of trig ratios, very simple one. And then sometimes we can get more complicated ones later in the semester. So let's take a quick look at what we mean by that. So the first thing we want to look at is we need to know what an angle of elevation is and what an angle of depression is. All right? So an angle of elevation, well, either of these angles, elevation or depression, you have to start with a horizontal line. Okay? Horizontal. All right? And you're looking horizontally. A lot of times what I like to do is put my arm out in front of my body, straight out in front of my body. And then if I raise my arm up, that's an elevation. If I drop my arm down, that's a depression. And so what I mean by that is if you raise your arm up like this from here, if you raise it up, then this angle is called an angle of elevation. If you go up from the horizontal. If you go down from the horizontal, so you drop your arm down, then that's what we call an angle of depression. Okay? Now, given that, what's going to happen is you're going to have some story problems that use these. So let's do an example here. So suppose there's a river flowing, and on the opposite side of the river is a tree, and you need to cut that tree down and, chop it so that that tree will fall across the flowing river, and you'll be able to walk across the river. But the problem is you need to know if this tree is tall enough. Okay? And all you have is an angle finder with you. So what you do is you come up to the tree and you set your angle finder on the ground. And so using that angle finder, you have it point to the top of the tree and to the base of the tree. And that then creates a right triangle. So let me draw that right triangle in here. There's your right triangle. And since it creates a right triangle, we have the angle that we can find with our angle finder here is an angle of elevation. If you see that? So typically this problem might say the angle of elevation from the ground to the top of the tree is, etc., etc. Okay? And so let's say our angle of elevation here was 40 degrees, all right? And then what we want to do is we want to be able to find the height of the tree, okay? But the only measurement we know is how far away from the tree we are. So let's say we're 30 feet away from the tree. All right. And so now can we find the height? So when you're given a problem like that, a lot of times what I suggest is you want to get rid of the extraneous information. So what you want to do is you just want to draw the right triangle and label what you know. This is 40 degrees, this is 30 feet, and this is X, the side you want to find. And so, since I know this angle, then this side is the opposite, and this side is the adjacent. So which ratio do I know am I going to use? I am going to use the ratio tangent. So I take the tangent of 40 degrees, and that is equal to the opposite side over the adjacent side. And now I can solve this, all right? I can put tangent 40 over 1, and then I can cross multiply, so I get x is equal to 30 times tangent of 40. And at this point, I can use my calculator to calculate the value. So it turns out I had to go get my calculator. Now, what was the rule I told you yesterday? Anytime you do a trig calculation on your calculator, so I'm getting ready to do a trigonometric calculation. So the first thing I need to check is my mode correct? All right, and so in this case, I need degree mode. So when I turn on my calculator, I notice my mode is radians. So I need to go to the mode. I need to change it to degrees. All right. And once I do that, I can proceed forward and do the calculation on my calculator. So I do 30 times the tangent of 40 degrees, and it gives me an answer that the height of the tree is 25.17 feet. All right. Now, if you were doing this on a quiz, they might tell you to round to the nearest hundredth, or they might tell you to round to the nearest tenth or the nearest thousandth. So whatever they tell you to round to, make sure you do that. That's an important part of what happens in trig quite a bit, is we need to round. All right. So what were sort of the steps I followed here? I'm reading the problem, and then they give me some information. So I often redraw the diagram, or I draw the diagram so I get rid of all the extraneous stuff in the way. And then from there, I choose an angle, and then I use that angle and an appropriate ratio with the side I want and the side I know. In this case, the appropriate ratio was tangent. Now, I could have written this as cotangent 40 equals 30 over x. Okay? And I would have gotten exactly the same answer. But look at your calculator. Look at all the buttons on your calculator. Is cotangent one of the buttons? The answer is no. It is not on the calculator. So if you were going to do it by cotangent, you have to remember that the cotangent is the reciprocal of tangent. So what you're really doing on this problem is you're doing 1 over tangent 40. And this is where those reciprocal rules come into play. So if you had seen this calculation on a problem, you have to think, well, I got to write that in terms of a calculator button so that I could actually use the calculator. And again, you'd cross multiply and you get x equals 30 times tangent 40. So you'd actually punch in exactly what we did here. Okay? So that's a little variation. But again, once you have these two sides, you can always pick whichever ratio you are using, tangent or cotangent. I almost always pick the ratios that are on my calculator. It makes my life easier. Alrighty? Let's go to the next. I want to mention briefly, as I told you, I'm copying a textbook and I'm going to put it in your class notes that you can use. And if you want more angle of elevation and depression problems to do and more challenging ones to do, what I want you to look at is you need to go to pages 151 to 160. So page 151 to 160. Those pages cover all the material that we are covering right now in section 2.3. So it'll be solving right triangles. It doesn't do the special angle stuff. That's in another section of the book, and I'll tell you where that is. But there are some more examples, and there are definitely more challenging problems in the exercises. And one other bonus I want to tell you about, when I finish copying this book, it has every odd problem answer in the back of the book. So you can also check your work that way. Alrighty. So the next thing I want to talk about is I want to talk about special right triangles. Do you remember what the special right triangles were from geometry class? Do you remember the measures of the angles? I'm going to try and draw them here just briefly. I'm going to draw a right triangle, and here's the right triangle, and these two sides are congruent. Okay, do you remember what the measures of those angles were? What about this one? Now, when I draw this one, it turns out the hypotenuse is going to be twice as big as the shorter leg. Do you remember what the angles were for this right triangle? Okay. Thinking. All right, let's see if you were correct. The angles were 45 degrees, and we called this, if you'll remember, a 45-45-90 triangle. That was the one that was isosceles. It had two equal legs. Okay? And this one, do you remember this one now? It was the 30-60-90 right triangle. And so 30 was the smaller angle, 60 was the bigger acute angle, and then, of course, the right angle. And so the smallest leg is opposite the smaller angle, and the shorter leg is half as long as the hypotenuse. All right? And then the longer leg had a measurement as well. In fact, let's do these. In the 30-60-90, if I said this side, the short side was S, then the hypotenuse was 2S, and the long leg would be S times the square root of 3. All right? In the same way, in the 45-45-90, if I were to say a side was X, then the other leg would be X, and the hypotenuse would be X times the square root of 2. And now these created ratios in the sides, and we would need to remember that. And here's an example of some problems we used to do with that. So in geometry, you might come to a problem, and somebody would say, hey, this leg is 5, okay? How long is the hypotenuse? And so because it was a 45, 45, 90, and you knew the hypotenuse was the square root of 2 times as long, you would just say 5 square root of 2. All right? Now, you could figure this out by the Pythagorean theorem. Since these legs are equal, they're both 5. So 5 squared plus 5 squared equals hypotenuse squared. 5 squared is 25, so you get 50 equals the hypotenuse squared. And if you take the square root of 50 and simplify it, that's actually 5 times the square root of 2. And so these lengths actually come from the Pythagorean theorem. Now, if you go to the 30, 60, 90 triangle, you could do the same sort of thing. What if somebody told you the hypotenuse? Well, they said the hypotenuse is 10. Well, then you could say, oh, the hypotenuse is twice as long as the shorter leg. So this is 5. And the longer leg is the square root of 3 times the shorter leg. So this is 5 times the square root of 3. And we would get all the lengths of those sides pretty squared away fairly simply. Now, this is what you should remember from geometry. But now we can sort of do this game using trig functions as well. Okay? So let's look at that. So suppose I had a 45, 45, 90 right triangle, and I wanted to find the length of the leg. Okay? Well, one of the ways I could do it is I could use the Pythagorean theorem. X squared plus x squared equals 20 squared, which is 2x squared equals 400, which is x squared equals 200, which is x equals the square root of 200, which is equal to 2 times the square root of 100. Or backwards, the square root of 100 times the square root of 2, which is 10 times the square root of 2. So I apologize for that error there. Okay? And this is how we did it probably in 8th grade. All right? In geometry class, we got so good, we'd know this, and we would know that if we had x here, then 20, this hypotenuse was the square root of 2 times x as large. So we'd know that x times the square root of 2 equals 20. And so we'd take x equals 20 divided by the square root of 2, and then we would rationalize our denominator, and that would be 20 square root of 2 over 2, which becomes 10 square root of 2. So notice how we get the same answer in either case. And this would be from a memorized procedure. We know the hypotenuse is the square root of 2 times the leg. So that's why I take square root of 2 times x and then set it equal to 20. All right? And in either case, we can find out what x is by solving. So now we get to trig. All right? And so what's the deal with the trig at this point? Well, what we would do is we'd say, oh, I've got a hypotenuse here, and I want to find the leg, and I'm going to call that adjacent. So what I would do then, let me redraw the diagram. I had something come up, kind of slowed me down. So let me redraw the diagram. All right. And so if I redraw the diagram, I get 45, 45, 90, and this is 20. And it's also the hypotenuse. And then I'm going to call this side the adjacent, and I want to find the adjacent, which is x. Okay? So that means I would end up saying the cosine of 45 degrees is equal to the adjacent over the hypotenuse, x over 20. Now, and this is very typically how we would write this out. And so then we would get 20 times the cosine of 45 degrees is equal to x. And then I could use my calculator to solve that out. Checking my calculator, I'm in degree mode, so 20 times the cosine of 45 degrees equals, and this would be 14.1421 ... equals x. Okay? Now, notice up here, I got 10 square root of 2 every time. So I got to check that. So 10 times the square root of 2 is equal to this. So this gives me the same answer. It also gives me a third approach to solving this problem, okay? But it also brings up an interesting issue. So the thing I want to tell you is that generally when we do problems that are in degrees, okay, that are in degrees, we always get a decimal answer, okay? And when we did kind of algebraic equations, we would get what we call an exact answer like this. So, but this is going to change in trig, all right? These special angles, which in trigonometry are considered 0, 30, 45, 60, and 90, and multiples of those angles, okay? All multiples, so like 120, 150, 108, etc. And beyond that, 900, all multiples, positive and negative, of those angles. Whenever you have these angles in degrees, or their compadres in radians, which are 0, pi over 6, pi over 4, pi over 3, and pi over 2. So, and all multiples of those, like 5 pi over 6, 11 pi over 6, 3 pi over 4, 2 pi over 3, negative 2 pi over 3, negative 4 pi over 3, etc. All multiples of those, okay? Whether in degrees or in radian form, whenever you see something like cosine of 45 or cosine of pi over 4, then you're going to want to write the exact value of that. So let's talk about how to do this. Okay, we have a lot to unpack here, and so we're going to do this for degrees, and then we'll move that up to other stuff in just a moment, to the radians, okay? So I almost finished this about 6 hours ago, so let me remember where I was. I want to talk about exact answers. We already know how to get decimals when we get sine of 45 or whatever, but how do we get exact answers? And the way we get them is we only get them for what are called the special angles from the special triangles. Most other situations, if it's not a special angle or a combination of a special angle, which we'll see in a later chapter, we're not going to get an exact answer. We're going to eventually write an approximation. Now, there are equations where we can get exact answers as well, but that's different than what this is. So one of the things you have to do in trig is you have to learn these exact ones, and you have to know them so that you can write them down every time when you see them. So for instance, when we see the sine of 45, we're always going to write 1 over the square root of 2 or the square root of 2 over 2 typically we write this one because it's got rationalized the denominator. So how do we find the sine of 45? Well, what we do is we pick any 45, 45, 90 triangle and label the sides, and I pick the one where the legs are 1, and then the hypotenuse is the square root of 2 times the legs. That's the geometry theorem. And so sine of 45 is going to be the opposite over the hypotenuse, which gives us the 1 over square root of 2, and then we rationalize the denominator and get square root of 2 over 2. We do exactly the same thing with the cosine of 45, get adjacent over the hypotenuse, and the tangent of 45, where we put opposite over adjacent. And so these are the simplified versions. So these, anytime you have a triangle with a 45-degree angle, you're going to write, and you want to find the sine, cosine, or tangent of 45 degrees, you're going to write this is square root of 2 over 2, or 1, depending upon whichever one you have. Okay? The same thing happens when we go over to the 30, 60, 90 triangle. And so if we take the sine of 30 degrees, that's going to be the opposite over the hypotenuse. So it's 1/2. All right? So we never write 0.5. Okay? We always write 1/2. All right? And then we can do the cosine of 30, which is going to equal the square root of 3 over 2, the adjacent over the hypotenuse, square root of 3 over 2, and the tangent of 30, which is going to be the opposite over the adjacent, which is 1 over the square root of 3, or if you wish, the square root of 3 over 3 after we rationalize. Now, we can also then, at this point, find the reciprocal functions, ratios of each of these. So the cosecant of 30 is going to be 2. The secant of 30 is going to be 2 divided by the square root of 3, which is 2 square root of 3 over 3. And the tangent, or cotangent of 30, is going to be the square root of 3. And so for all these special angles, we could do this. So in the assignment, I'm going to want you, likely, they're probably going to have you do in the lessons, do like the sine, cosine, and tangent of 60 degrees. So I'm going to let you do those on your own. But I want to show you something really special here, because we have to memorize these. And there are a couple of ways you could do that, and I'm going to show you both, and then you decide what you want to use, although you need to know both. All right? So last thing for this lesson. So one of the ways we think about this is we take a circle and we center it on the origin. And then what we do is we slowly divide that circle up, first into eighths, and then we divide it by the 30-degree angles, 30 and 60, 120 and 150, 210, 240, and 300, and 330. And so those are our angles. So we go 30, 45, 60, 90, all the way around. So when we have 0, we're going to need to know what the sine of 0, the cosine of 0, the tangent of 0 are. All right? And then as we move around the circle, here we want to know the sine of 30, the cosine of 30, and the tangent of 30. And we don't want to know these as calculator answers. We want to know these as exact answers with the radicals in them. Okay? And then, of course, we'll do the same thing. Sine of 45 plus the rest. Sine of 60 plus the rest. And a sine of 90 plus the rest. Now, we're going to talk about some of this, the rest of this tomorrow. But as you go into quadrant 2, the ratios change. not their value, but their sign. So when we get to 120 degrees or 2 pi over 3, it's in a different quadrant. So the sine of 60 might have the same value, or it might have the same value with an opposite sign. Okay. And so as we move around, we're going to learn something about the quadrants and the values of sine and cosine. All right. And so that's going to be a really, really important thing that we're going to see here as we move along. And so you can create a circle like this. A lot of people take a paper plate or a round sheet of paper that they make with a compass. So they get a nice circle, and they draw the perpendicular diameters through the center, and then they actually measure off 30 degrees, 45 degrees, 60 degrees, etc. And then in addition, then they'll label, so you'll have 0 degrees and 0 radians, 30 degrees and pi over 6 radians, etc. So they label the radians, and then they'll put the values of the functions by them. And they'll do that like on a paper plate in a circle, and then keep it, and that's part of your notes. But I have a secret for you. And shockingly, I read this out of a professional publication way back in the 1980s. All right. I was reading what was called the American Mathematical Monthly. Oh, I know, total nerd fest right there, right? Well, I was into math. I was thinking I was going to be a research mathematician once upon a time. And they published research mathematics in here. But every once in a while, they publish things about things you could use in life, or interesting little tidbits. And one of them they published was a way to remember all these values. And so I'm going to show you the basics of it, and then I'll show you more with it later. But the basics are this. What you do is you label the angles on top. So you put them in order: 0, 30, 45, 60, 90. And then you label the radians: 0, pi over 6, pi over 4, pi over 3, and pi over 2. And then you write the functions: sine, cosine, and tangent, just in that typical order. Now, here comes the interesting part. Every one of these things is divided by 2. Divide by 2, divide by 2, divide by 2, divide by 2, divide by 2. Really? They're all divided by 2? The answer is yes. And even better than that, they count up by numbers. So you go 0, 1, 2, 3, 4. Like that. And then, last step, you take the square root of the numerator. Now, all those are there, so I'm going to get my eraser. But the square root of 0 over 2 is just 0. The square root of 1 over 2 is just 1/2. Square root of 2 over 2, remember that from the sine of 45. Square root of 3 over 2, remember that from the sine of 60. All right, and then square root of 4 over 2 is 2 over 2, or just 1. So let's fix that one as well. This should be something in your notes. Now, because cosine is the cofunction of sine, then the complementary angle is going to have the value. So the 0 degree angle for cosine is complementary to the 90 for sine, so the cosine is going to be 1 there. And these are just going to be listed backwards because of our cofunction principles. Pretty cool. And the tangent, I don't know if you have noticed it, but if sine is opposite over hypotenuse and cosine is adjacent over hypotenuse, when you take the opposite over the adjacent, that is exactly the same thing as this one divided by that one. Numerically. Go ahead, work it out. Division. So all I have to do is think of this, the top row as the numerator and the bottom row as the denominator. 0 over 1 is 0. 1/2 over square root of 3 over 2 is 1 over the square root of 3. Square root of 2 over 2 over square root of 2 over 2 is 1. Square root of 3 over 2 over 1/2 is square root of 3 over 1, or just square root of 3. And, excuse me, I hit my thing. And 1 over 0 is undefined. Sorry, let me write that. Undefined. Okay, now this whole thing I've done here is kind of a bonus, but this is something you want to hang on to and remember or keep in your notes. Trust me, it'll be helpful. So one more thing we'll do really quick here. We'll add one more page. One of the things they wanted you to do was in the assignment would be like a weird thing. They'd say, why don't you find the perimeter of this square if you know that the diagonal is equal to like the square root of 10? Okay? So how would you do a problem like that? Well, because it's a square and you have a diagonal, this is a 45, 45, 90 triangle. And I know that the hypotenuse is the square root of 2 times the leg. So that means I need to divide this hypotenuse by the square root of 2. So the square root of 10 divided by the square root of 2, that's going to be the leg, or the leg is just square root of 5. Well, so the whole square, everything is now the square root of 5 for the legs. And if I add up each side, that's the perimeter. So the perimeter is 4 times the square root of 5. And you can use 30, 60, 90s to do this or whatever else. So, but this is kind of an approach to the problem. If you're stuck and you can't use the 45, 45, 90 theorem from geometry, you could just say, oh, I want to find the leg, so it's x, so I'll call it x, and I can go, oh, the sine of 45 degrees, this one, is adjacent over hypotenuse, or, excuse me, not the sine. Adjacent over hypotenuse is cosine of 45 is equal to x over the square root of 10. And the cosine of 45, I already know, is the square root of 2 over 2. See, this is where knowing the exact helps you. You don't have to use a calculator. And that's equal to x over the square root of 10. All right? So then I can cross multiply, and I get the square root of 20 equals 2x, like that. And then square root of 20 is 2 square root of 5 equals 2x. And then you divide by 2, and you get the square root of 5 equals x. So you can see this, doing it with trig, you're going to get quite the complicated problems where you got to really know how to manipulate. And so, see, we can get the same x value even if I didn't know the 45, 45, 90 theorem. Okay? And this is a case where we use an exact answer in the problem and not a decimal. So you have to remember that about those angle sizes. 30 degrees, pi over 6, 45 degrees, pi over 4, and any multiples of those, all right? All the way through, okay? So that's all I have for you. Good luck. Enjoy this video.